So let us continue with ensemble methods, right? Like, so before the break, we looked at the idea of bagging. Okay, so where we typically combine a set of m different models, like where all the models are sharing the same inductive bias, right? If you're bagging a bunch of logistic regression model, or you're bagging a bunch of k-nearest neighbor model, or you're bunching a bag of linear regression models, etc. Right? So the idea of bagging is to construct k different models and just take an average. Right? So in some sense, you could construct all these different models in parallel and just take an average of them during prediction. Okay. So now we are going to look at a second family of ensemble methods. Okay, so this is called boosting. Okay, so the idea of boosting was invented by Froome and Schaffer, 1996. Okay, so boosting is similar to bagging in the sense we are going to construct m different classifiers and take an average or weighted average of these m different classifiers. Okay, however, it's different from bagging in the sense we're going to construct these classifiers sequentially, okay, one at a time. Is that clear? Okay, so I'll start with a very high level picture of boosting, so then we're going to get into the technical details. Okay, so typically we will assign some weights to each example in the data set, and we're going to use these weights to somehow tell which example is important to learn. Okay, and we're going to train one classifier. Let's just call it y1 of x. Is that clear? So this is basically the weights of data set, and this is my classifier. Is it clear? Now, after I finish training the first classifier, then I'm going to reassign the weights for each example. So I'm going to get a new set of weights, wn of 2. Okay. Now, the crux of this algorithm is in how you assign these weights. Okay. So I'm going to assign weights in such a way that the examples that are correctly classified by the first classifier is going to get less weights, and examples that are wrongly classified by the first classifier is going to get high weights. Okay. So this way, when I train the second classifier, y2 of x, okay, so this classifier actually is trained to concentrate on the mistakes of the first classifier. Is that clear? So I train the first classifier, then I'm going to train a second classifier which focuses on the mistakes of the first classifier. So then I repeat this process again. So I'm going to come up with wn3, sorry, same color. So wn3, and this wn3 is based on the mistakes of the previous two classifiers, right? Like, and this is going to give me y3 of x, okay? And I just continue this process for a bunch of time, and eventually I get wnm. This is going to give me a classifier ym of x. Okay. So this is a sequential process, right? Like, well, of course, we are going to discuss in detail how to construct these WNs, like how to combine these models and all those things. But first, I want you to get the idea of boosting. Okay, the idea of boosting is to first train a model y1 of x with a bunch of weights for the examples. Then look at the mistakes of y1. Then you train y2 of x, where the weights of this model's importance for the examples is decided based on the mistakes of y1. Okay, so any example where y1 makes mistake, the weight is increased. So any example where the y1 makes no mistake, like the weight is reduced. Is that clear? So then y3 is focusing on the mistakes of y2. Y4 will focus on the mistakes of Y3 and so on. Finally, Ym will focus on the mistakes of Ym minus 1. Is that clear? So what happens here is each successive model is learning from the mistakes of the previous model. Now, finally, I could just combine all these models together. Okay, the way in which I'm going to combine these models is Ym of x. Okay, so this is going to be y capital M of x, just to say that this is combination of all the M models, is given by sine of summation M is equal to 1 to capital M alpha M Ym of x. So I'm basically doing a weighted average of all these predictions where the weight is given by alpha M. Okay, we will talk about how to construct and come up with this alpha M. And by sine, I just mean like, oh, I'm going to pick the maximum. This is like +1 -1 classification. So if the sign is positive, then it is class 1. If it is negative, it is class -1. Is that clear? Is the idea of boosting clear? Like, any questions so far? So there are still a few missing details here.
Can you still? I didn't understood the last part. Why is the sign?
Oh, the sign is because this is kind of like majority voting, right? So you have m different classifiers, right? You're combining their prediction. If this prediction is positive, I'm doing the classification here, like it's +1 -1 classification. Okay, so the task is +1 -1. So the sign just means that, oh, if you get a value which is like +49, then the class is +1, because we just need to look at the sign, right? So if you are getting a value which is like -5, then the class is minus, like -1. Is that clear?
Yeah. Okay. Thanks.
Okay. So can someone tell me what are the missing details here? So if I have to implement this algorithm, what are the missing details?
Can you repeat the question, please?
So what are the missing details in this picture if you have to implement boosting?
How to update alpha?
How to compute alpha? Yes, we don't know how to compute alpha. Anything else? So there's another big missing info.
How do we assign the weights?
Yes. So there are two missing pieces here, right? So one is, how do we assign these weights, right? I told you that like you should use the mistakes of the previous classifier so that you increase the weight whenever the previous classifier makes a mistake, right? But I haven't given you a specific formula to do that, right? Like so the first missing piece is like, how do we compute the weights? The second missing piece is, how do we compute alpha? Is that clear? So once you have these two information, you should be able to implement this algorithm, right? Before we look into these two details, right? Like, so one thing to remember is this is a sequential process. And the most important part here is each classifier is learning on the mistakes of the previous classifier, right? So which means there is actually significant chance of overfitting. Like, so if you have a very powerful classifier and it is just learning from the mistakes of the previous classifier, then there's a very high chance of overfitting. So you have to be careful when you're boosting. Typically, people would boost weak classifiers or classifiers which are not too powerful. Okay, if your classifier is too powerful, then it can easily overfit through this boosting process. Is that clear? Which is kind of very different from bagging, because in bagging you have 10 different models and you're taking the prediction of all these 10 different models and take an average, right? You don't want weak classifiers there. You actually want very powerful classifiers. Like, you want each model in bagging to be too good so that you can get the benefit of bagging. But to get the benefit of boosting, you just need to use like simple classifiers. Is that clear? Any question? Okay, so now let's look at the details of the algorithm, right? Like, so first I'm going to write the algorithm. Oh, sorry. Okay, so first I'm going to write the algorithm. So then we will derive things from first principles. Okay, so the algorithm, the variant of algorithm that we are going to discuss in today's class is called AdaBoost. Which basically stands for adaptive boosting. Okay, this is how the algorithm looks like. So first, I'm going to initialize the weights. Okay, the way in which I'm going to do this is, because I'm just getting started, I'm going to give same weight to all the examples. I'm going to give the weight of 1 by n for all the examples. So this is intuitive, right? Like, so I have n examples. I have no prior knowledge about the difficulty. So I'm just going to assume that the weight for each example is 1 by n. Is that clear? Okay. Now, for m is equal to 1 to capital M, right? Like for each iteration of the boosting process, first I'm going to fit a classifier ym of x to the D train by minimizing this objective function. The objective function I'm going to use is the weighted objective function. So summation m is equal to 1 to capital M Wn of m times the indicator function ym of xn not equal to dm. So I'm trying to minimize this function. What does this function say? This says, because this is an indicator function, this is going to be 1 whenever ym is not equal to tm, right? So whenever the model makes mistakes, it is 1. So in some sense, this is like 0 on classification, okay? And for each error that the model is making, I actually have a weight. So it's weighted error, and I'm trying to minimize this weighted error. Is that clear? So once I do this minimization process, then I'm going to evaluate two different things. Okay, I will tell you later how I came up with these two different things. Like, so for now, let's just say I'm going to evaluate epsilon m, which is summation n is equal to 1 to capital N Wn of m indicator function ym of xn not equal to tn divided by summation n is equal to 1 to capital N Wn of m. Okay. Similarly, alpha m is given by log 1 minus epsilon m by epsilon m. Okay. I'll tell you how I came up with these two terms later, but for now, let's try to understand intuitively what these terms means, right? Like, so the first term, the denominator of the first term is the total weight for the data set, right? And the numerator of this first term is the summation of all the weights only for examples where the model makes mistake. So what is epsilon m then? Epsilon m is basically the ratio of the weight for the mistakes to the total weight. So in some sense, it's the error, but in the weight space, right? So that is epsilon m. Then what is alpha m? Alpha m is basically the log odds ratio of the error versus the correct prediction of the model. So 1 minus epsilon m is going to be the weight of all the correct predictions. Epsilon m is going to be the relative weight of all the incorrect predictions. Is that right? Okay. Let's take these two things for granted right now. Like, I'll tell you how to derive these things, right? So once I have these things, then I'm going to update the weights. Okay. So update the weights So WNM plus 1 is given by WNM x of alpha m, the indicator of ym of xn not equal to t. Okay, you see how I am updating the weights, right? Like, so for the next round, I'm updating the weights by multiplying the current weight with x of this thing. Okay, so whenever the model is making mistake, I'm scaling the weight by x of alpha n. Is that clear? So the end effect is whenever the model makes mistakes, the weights are increased. And for examples that are correctly classified, there's no change in the weight. So relatively, the weights of the mistakes increase over time. Is that clear? So once I do this step for m different times, like finally I'm going to do the prediction from the model, which is y capital M of x, which is given by sine of summation m is equal to 1 to capital M alpha m ym of x. The alpha m is given by this thing. Is that clear? Any questions so far? Okay, so now the algorithm is complete. Yeah.
Yeah, I wanted to be clear. What is the pi of yn? Is it plus tn?
Which one?
Um, the term on the exponential in the exponential, it's alpha m pi of ym of x,
It's
right?
not. It's not pi. It's the indicator function. So
Indicator
this
function, okay.
is indicator function. Okay. So maybe for people who don't know the indicator function, right? Like, so the indicator function a not equal to b is going to be 1 if a is not equal to b. It's going to be 0 if a is equal to b.
Okay. Thank you.
Okay. Okay. I think now you can implement this algorithm, right? Like, so if I ask you to implement AdaBoost, you should be able to implement it because the algorithm is clear enough, right? However, there are a few magical things here, right? Like, so for like, I think the most importantly, how did I come up with this epsilon m alpha m, which plays the critical role in updating the weights and combining the classifier, right? So we're going to do this derivation, right? Like, so before that, let's look at an example. So here is an example of boosting, okay, where the individual classifiers I'm going to use for boosting are called decision steps. Okay, so what are decision stumps? Decision stumps are really simple decision tree, but there's only one node. Okay, there's just one node, one test. That's it. That is the classifier. So this is an example of a weak learner. It's a weak learner because it's not very powerful, right? Like, so it's just one tree. Is that clear? Like, it's just a tree with single root node. Okay. Now, how does decision stump works? So let's start with this example, right? Like, so we have a bunch of examples here, circles, like red circles and blue circles, right? And I want to classify the red circles from blue circles. Okay. So initially, I start with equal weight for all the examples. So that's why you see the sizes of the circles to be in same color, like same size, right? So I fit a decision stump which says, oh, I'm going to split the data here. Okay, anything that is in the right is red color. Anything that is in the left is blue color. Okay, now after the first decision stump, we're going to look at the different errors that the model has made. Okay, what are the different errors? Right? So for example, this is an error. right? So this is red color, but it is in the blue region. So this is another error. This is another error. This is another error, like the blue in the red region. This is another error, right? So now you see, when you start training the second model, the sizes of the circles of all these mistakes are bigger, right? I have increased the weight for bigger, like for things which are mistakes, right? So now I'm going to train a second classifier. The second classifier does the classification here. Okay, so the effect of these two, when I combine these two classifiers, I'm going to get a classifier like this. Is that clear? Now there are still some mistakes. So you're going to focus on these mistakes, and you will keep repeating this process, and eventually you're going to get a complex decision boundary. Now, this is after 150 iterations. Okay, so the benefit of using weak classifiers is you can just have as many classifiers as you want, and you're not going to overfit. Is that clear? Any questions so far? Okay, so now let's go back to the Adabos algorithm, right? Like, so how do I came up with epsilon m and alpha m, which is used in this Adabos algorithm? Okay, so to do this, I'm going to introduce a new type of error function. Okay, this error function is called exponential error function. But before I do that, as a quick recap, can someone tell me all the different error functions we have seen so far in this course?
Least squares,
Yeah,
means-
we have least squares, yeah.
RMSE.
Well, that's least squares.
Well, that's good.
Yeah. Anything else? So what other error functions we have seen so far?
Log likelihood.
Log likelihood, like the NLL, right? Negative log likelihood. Yeah. You can also call this as cross entropy, right? So any other error functions?
Huber
Hinge
loss.
loss.
Sorry, what?
Hinge
What was
loss.
it? Hinge loss, yeah. I think someone said Huber loss, right? So, well, we haven't looked at it in detail in the class, but yes, Huber loss or L1 loss. Huber loss is just a combination of L1 and L2. Okay. And most importantly, the 0-1 loss, right? So these are the bunch of loss functions that we have seen so far, right? Like, so now I'm going to introduce a new error function called exponential error function, which is given by the error is summation n is equal to 1 to capital N. The error is defined as exponential of minus Tn times Fm of Xn. Is that clear? So it's minus Tn times Fm of Xn, and I'm taking an exponential here. And what is Fm of Xn? Fm of, Xn is given by 1 over 2 summation L is equal to 1 to capital M alpha L YL of X. So this is just the boosting algorithm, right? And the target is either -1 or +1. Is that clear? So now this error function gives exponential loss or exponential penalty whenever the model makes a mistake. Okay, so now I want to minimize this error, but then there are two different parameters that I have to minimize for. So one is this alpha L, the other is the parameter of the classifier. Okay, so the goal here is to minimize E with respect to alpha L and the parameters of YL of X. Is that clear? This is not an easy thing to do, by the way, okay, because we are trying to minimize the error with respect to two different things. Like one is the weight that you're giving to the classifier, and simultaneously you also want to minimize it with respect to the parameters of the classifier itself. Is that clear? Okay, so let's see how to do that. So the error function is given by summation n is equal to 1 to capital N x of minus Tn Fm of xm, right? Now the idea with boosting is I'm going to minimize this error function sequentially. Like I'm going to do this for the first classifier, then for the second classifier, then for the third classifier, right? So to do this sequentially, it's going to be easier if I split this error function into my current error and the previous error. So I'm going to write this as summation n is equal to 1 to capital N x of minus Tn f m minus 1 of xn minus 1 over 2 Tn alpha m ym of xn. Is that clear? So what have I done here, right? So I have split the model's prediction fm into fm minus 1 plus the last prediction, which is given by 1 over 2 alpha m ym of xn. Okay, so this I can write as summation n is equal to 1 to capital N WNM times x of minus 1 over 2 Tn alpha m ym of xn, where Wm n is x of minus Tn fm minus 1 xn. Okay, so I'm just giving a name for this thing because when I'm minimizing with respect to the mth classifier, I don't need to touch this part. Is that clear? Any questions so far? Okay, so let me rewrite this, right? Like, so the error is given by summation n is equal to 1 to capital N Wn of m x of minus 1 over 2 Tn alpha m ym of x. Okay. Now I'm going to consider two different sets of examples, tau m and mu n. So tau m is basically the set of data points that are correctly classified by ym of x. Okay, and mu m is basically the set of data points that are misclassified by ym of x. Okay, so given a bunch of data points, I'm going to divide it into two groups. One is tau m, which is all the data points that are correctly classified, and the other is mu m, which is basically all the data points that are misclassified. So now I can split the error also into two parts, right? Like, so the error for the correctly classified examples, the error for the wrongly classified examples. So the error can be written as e power. Okay, so whenever the example is correctly classified, for correctly classified examples, Tn times ym is going to be 1, right? For wrongly classified, it's going to be -1. So for correctly classified examples, this is basically e power minus alpha m by 2 summation n belonging to tau m wn of m. Is that right? Now for wrongly classified example, this is going to be e power. So this is going to become minus, so minus into minus is plus. So it's going to be e power alpha m by 2 summation n belonging to mu m wn of m. So all I have done here is I split the error function into two different parts. So one is the error for correctly classified examples, and the other is the error for misclassified examples. Is it clear? Okay, let me copy this to the next line. So I'm going to do a few modifications here, okay, with some basic algebra. So let's take let's take this miscorrect, like misclassified examples, right? So we have e power alpha m by 2, right? I'm going to subtract e power minus alpha m by 2 summation n is equal to 1 to capital N wn m, the indicator function ym of xn not equal to tn, plus e power minus alpha m by 2 summation n is equal to 1 to capital N wn m. Okay, so what have I done here? So all I have done is with the first term, right? With this first term, which was just for correct examples, I also added the incorrect examples. So which means then I should subtract it back, right? Like, so which is what I'm doing with this. So I'm doing plus and minus e power minus alpha m by 2, basically. Okay. So with this trick, we have an error function which looks something like this. Okay. This looks like a complex error function, but it is not. So let me copy this error function to the next. Oh, sorry. Let me copy this error function. Okay, why is it not working? Oh. Okay, let me try once again. So let me copy this error function to the next line. Okay, if I want to minimize this error function with respect to, let's say, ym of x, I want to minimize this error function with respect to ym of x. Okay, now look at the error function. The second term that you see here, this is actually not a function of ym of x, right? So when I'm minimizing with respect to the parameters of ym of x, I can just ignore the second term. Even in the first term, this multiplier is independent of ym of x, right? Which means if I want to minimize e with respect to ym of x, then I just need to minimize summation n is equal to 1 to capital N w n of m indicator ym of xn not equal to t. Is that right? So this is exactly what AdaBoost is doing, right? Like in AdaBoost, at every stage, we are trying to minimize this function. Now we are just seeing that this is actually the principled way to do it if you consider exponential error function. Okay. Now the next thing is to differentiate this error function or minimize this error function with respect to alpha m. Like then we are going to derive alpha m. Is that clear? Any questions so far? Okay, I think we can take a break here. So after the break, we're going to take this error function, differentiate it with respect to alpha m, and that would give us the missing details of the AdaBoost algorithm. Okay, so let's take a small break.